Welcome to the online narrated lectures for CM2101. In week 6 we will finish our discussion of rotational spectroscopy by looking at polyatomic systems. However, in order to do that we need to discuss symmetry and introduce some basic ideas from group theory. This will enable us to classify polyatomic molecules and thus identify some of the selection rules that arise as molecules become more complex. We will continue our discussion of group theory later in the lecture course, after we have discussed some of the elements of vibrational spectroscopy. We will see, for instance, that group theory can be used to identify which vibrations are infrared active in the same way as possession of a permanent dipole moment is a prerequisite for a molecule to be microwave active. We are very familiar with the concept of symmetry. It occurs in nature. Here we see a snowflake with near perfect six-fold symmetry. And of course we do ourselves possess bilateral symmetry, just as this Arctic tern does. This symmetry is present in all animals of the bilatera subregnum and is part of our shared evolutionary heritage. Symmetry plays a profound role in art. It is probably in Islamic art, such as this example, that the use of symmetry in art found its zenith. Symmetry is of course also important in crystals. But this one here is rather unusual in that it possesses five-fold symmetry. This is the holmium magnesium zinc quasi-crystal. Its discovery in 1982 by Dan Shechtman won him the 2011 Nobel Prize in Chemistry. In fact, the non-repeating five-fold symmetry possessed by this crystal was anticipated several centuries ago by Islamic architects. Let's listen to this music being played by Cyrus Berakim and Jennifer Cho. Can you hear the symmetry? This is a piece of music which is attributed to Mozart known as table music for two, and here it is. You can imagine this music sheet placed on a table between two violinists. This piece of music is designed such that one violinist starts at the top, and because the second violinist is on the opposite side of the table, he or she starts at the bottom and plays the music upside down compared to the first violinist. This involves symmetry. Mozart used symmetry to create a piece of music that can be played by people facing each other with the musical score on the table in front of them. So symmetry can occur all over the place. So I'm going to have a look at how we can quantify symmetry. Which objects, for instance if I look at these objects, a sphere and a cube, which is more symmetrical? I think that we would all agree that the sphere is more symmetric. Why do you say the sphere is more symmetrical? Intuitively you know that's right, but what is it about the sphere that makes it more symmetrical than the cube? If I put my rotational axis through my sphere, it doesn't matter what angle I rotate it by, the object looks exactly the same. For the cube, however, this is not quite the case. I could put a rotational axis through the centre of the front plane such that it passes through the centre of the back plane, and clearly I could rotate it by 90 degrees and return to the original position. When we talk about symmetry, we frequently refer to symmetry elements. What is a symmetry element, and when do we know that an object possesses a specific symmetry element? Basically, an object possesses a symmetry element if after performing the symmetry operation associated with the symmetry element, you cannot tell if a symmetry operation has taken place. If I can't tell whether you've done a symmetry operation, it is a symmetry element. So in the case of the cube, if you rotate by 90 degrees and I am not looking while you are performing the rotation, then I wouldn't know if you performed the rotation unless I labelled the corners. You can also rotate it by 180 degrees, or in fact 270 degrees, and they are also symmetry elements of the cube. What is not quite so obvious perhaps is that there is also a threefold axis in a cube, in fact several threefold axes. Do you see the threefold axis? A threefold rotational axis is one where you rotate by 120 degrees. That is 360 divided by 3. So I can rotate it by 120 degrees and return back to the original shape. It is a little bit more tricky to visualize, but perhaps if you've got a cube at home you can play around with it. If you try to look down the corner of the cube, you may see that there are 3 corners visible that form an equilateral triangle. So the cube has lots of mirror planes, lots of 4-fold axes, 2-fold axes, and has quite a few 3-fold axes as well. There is a lot of symmetry involved in a cube, but of course not as many as you have in a sphere, which has an infinite number of rotational axes. So that is an obvious one. Obviously a sphere is more symmetric, and we are getting a feel for why it is more symmetrical. It has to do with the number of symmetry elements. What becomes a little more tricky, for instance, is if I asked you this question: which of these 3 molecules is more symmetrical? Which is the second most symmetrical, and which is the third most symmetrical? Again, I think it's quite obvious. The first one certainly has 2-fold axes and a few mirror planes, so it possesses quite a few symmetry elements. The next one still has got one of the 2-fold axes, but the vertical one has disappeared. It's got one mirror plane going through here, but the one that was bisecting the carbon-carbon bond in this molecule here has gone. So it is less symmetrical than the ethene molecule. The third one, however, has lost a lot of symmetry elements. In fact, the only one remaining is the horizontal mirror plane, the mirror plane in which all the atoms lie. It will leave the atoms the same after performing such a symmetry operation, so it still exists. So it still has symmetry elements, but clearly not as many as the others. So the degree of symmetry has decreased as I go from left to right. How about these though? And in fact you can include the centre molecule from the top as well. Which of those 3 is more symmetrical? Now it is more difficult, very difficult to determine, but clearly they have different symmetries associated with them. And identifying what those symmetries are enables us to say something about the rotational vibrational structure of the molecule, and you will see at the end of this course the importance of symmetry in the electronic structure of the molecule. What we certainly need is a more systematic way of defining symmetry. I think we are getting closer to that. We've identified it has to do with identifying symmetry elements, rotational axes, mirror planes, as well as other symmetries that might not be as familiar to you. So what is it, then, this thing I call a symmetry operation? A symmetry operation is any proper or improper rotation, reflection or inversion that leaves the system unchanged. Now remember, if you want to know if it is a symmetry operation, perform the following test. Look at your object, turn away, perform the symmetry operation, turn back. Has it changed? Can you tell me, assuming you haven't labelled the atoms, can you tell whether a symmetry operation has taken place? If you can, it's not a symmetry element. If you can't, it is. So some of these symmetry operations I have mentioned here are familiar. For instance, a proper rotation is one that you are familiar with. Improper, probably not. What do I mean by that? We will discuss that in a little while. Reflections, I'm sure that you understand mirror planes, and I think you'll probably have a good idea what an inversion is as well. Now we are going to be looking at what is known as point group symmetry, and these are the symmetry elements associated with the centre point of the molecule. So for the sphere, of course, the centre of symmetry is the centre of the sphere. For the cube, it is the centre of the cube. For the ethene molecule, it would be the point that bisects the carbon-carbon bond. So because we are interested in the symmetry around the centre point of the molecule, these are known as point group symmetries. And in total, there are 5 kinds of symmetry operation. We need to have, partly because of the mathematics, which I'm not going to go into details about, a special symmetry element which is known as the identity and is given the symbol E, which is do nothing. You can also consider it to be a rotation by 360 degrees. We need this symmetry element for the mathematics of group theory to be complete. We've also got the n-fold rotation with this label C sub n. So a two-fold rotation is where I rotate by 360 divided by 2, that is by 180 degrees, hence a two-fold axis. Every time I rotate the molecule through 360 degrees, I return to the same point twice. This symmetry element has been given the symbol C sub n, so C2 is the two-fold rotation axis. We've also got reflection planes, and they've been given the symbol sigma. We've also got an inversion axis, which has been given the symbol I. Don't get it confused with the identity. The reason why the identity has been given the symbol E is because the Germans got to symmetry before we did, and for them, eigen means equal, and so they use E for the identity symmetry element. And finally, we have our improper rotation axis, and I'll describe them in just a little while. They've been given the symbol S sub n. An n-fold rotation looks like this. It is essentially, as I said, 360 degrees divided by n. That's where the n comes in. So in the water molecule on the left, we have a C2 axis. If I rotate by 180 degrees, I'm exchanging my two hydrogen atoms. My molecule looks exactly the same after that 180 degree rotation. In the ammonia molecule in the middle, we have a C3 axis. If I rotate by 120 degrees, my molecule will look exactly the same. And finally, I've got a sulfur hexahydride molecule, which has a C4 axis, and so I can rotate by 90 degrees and the molecule looks exactly the same. So this symmetry element, the proper rotation, has the symbol C sub n. And note, of course, that a C1 rotational symmetry operation is equivalent to the identity. Rotating by 360 degrees is the same as the identity. Let's have a look then at a different molecule. This is a methane-like molecule, a tetrahedral molecule. And notice that tetrahedral molecules, like methane, can fit within a cube. So notice how that works. If I put two of my hydrogen atoms diagonally opposite on the top face of the cube and put my other hydrogen atoms diagonally opposite but on the other vertices on the bottom face of the cube, my carbon atom will lie in the exact center of the cube. We all know that the bond angles in methane is 109.5 degrees, or more accurately 109 degrees and 28 minutes. Well, that is not very easy to calculate, but it will be easy if you set up your system like this, and then you can use simple geometry to work out what these bond angles are. And now, hopefully, you can see indeed that a cube does have a threefold rotation axis. You can see that if I rotate around this C3 axis by 120 degrees, the three atoms not on the axis will permute with one another, and that indeed this is a symmetry element of the molecule. You will notice that if I rotate around this axis here, this atom will go to this position, this atom will go to this position, and this atom will go to the position of the first atom. Similarly, the axis which is perpendicular to the plane of one of the surfaces is a C2, or twofold axis. If I rotate by 180 degrees, this atom here will go to here, and this atom will go to here, and vice versa. So tetrahedral molecules like methane have C2 and C3 axes. This molecule is a hydrogen cyanide molecule, and it possesses a C infinity axis. In fact, all linear molecules have this C infinity axis around the internuclear axis. I can rotate about any angle around the internuclear axis and the molecule will look unchanged. We can see that some molecules have rotation axes with different values of n. For such molecules, we can define the principal axis, which is the axis which has the greatest value of n. So for methane, the C3 axis is the principal axis. It is not how many C3 axes or how many C2 axes the molecule has that defines the principal axis, but the axis with the greatest value of n. So if a molecule has a C4 axis, like gold tetrachloride, that would be the principal axis in that system. A molecule like benzene, for instance, has a C6 axis, and that is the principal axis. It also has a lot of C2 axes as well, but the principal axis is the one with the highest value of n, the C6 axis. So I'm just giving you ways of describing symmetry elements and molecules. We've also got reflection. Here is, say, a gold tetrafluoride molecule which has a square planar symmetry. It has a horizontal mirror plane. A horizontal mirror plane is one that is perpendicular to my principal axis and is labelled sigma h. Clearly this molecule has a C4 axis and C2 axes, but the C4 axis is the principal axis. So therefore I am able to describe the horizontal mirror plane in the system because it is perpendicular to the principal axis. There are also mirror planes in the molecule. Here is a set of them. These actually go through the atoms themselves, and I've labelled them sigma v and sigma v prime. The only reason the prime is there is to distinguish between the two. Now wait, you have probably noticed that there are more mirror planes than that, and indeed there are. I have these mirror planes here which bisect the fluorine-gold-fluorine bond angle, and these are labelled sigma d for dihedral. You don't need to worry too much about that. In fact, if you confuse the d with the v, the mathematics will work out in the end, but this is the convention that is used. I won't mark you wrong, for instance, if you get this mixed up. It is not something to be desperately worried about. It is more important that you identify the mirror plane rather than if you have precisely labelled them with the correct convention. And indeed, unfortunately in group theory, the chemists and the physicists disagree with how they label these symmetry elements, so it is not as if you would be alone in the community. So what is reflection? To define it properly, it is the action whereby the reflection through the plane to an equal distance on the opposite side produces the same structure or configuration. So we have the sigma v mirror planes which are parallel to the principal axis, and also the sigma d mirror planes which are also parallel to the principal axis, but they bisect the C2 axes which go through the atoms of the molecules. There are also, of course, C2 axes which lie within the sigma d mirror planes as well. Hopefully you can see some of these. And finally, there is a sigma h mirror plane which is perpendicular to the principal axis. Here is a sulfur hexafluoride molecule which has an octahedral shape. Why is it called octahedral, by the way? I only have 6 fluorine atoms, but I call it octahedral. Octa meaning 8. So why do we call it an octahedral shape rather than a hexahedral shape? Well, the point is, it is not the number of vertices I have in my shape, but the number of surfaces I have that is important. So I have 8 surfaces, but 6 vertices. And here I've got my benzene molecule, and here I have a special molecule, mesotartaric acid. These all have centres of inversion, and an inversion is defined formally as the translation of each nucleus through the centre to an equal distance on the opposite side, and if that produces the same symmetry and configuration, the molecule possesses a centre of inversion. So I have a centre of inversion here in the sulfur hexafluoride molecule. If I apply the inversion symmetry operation, this atom, say here, will go to this one to here, and this one to here. Similarly, I have a centre of inversion in the benzene molecule here. And I also have a centre of inversion in the mesotartaric acid molecule here. On inverting this molecule, we see that the carbons go to the opposite carbon, the oxygens to the opposite oxygen, and the hydrogens to the opposite hydrogen. Rather unusual, this molecule, because for this molecule the centre of inversion is the only symmetry element it has. Not many molecules just have a centre of inversion. Now the next one is slightly confusing. Here we have a tetrahedral molecule. It is called tetrahedral not because it has 4 points, but because it has 4 sides. There isn't a C4 axis, but if we apply the C4 rotation and then we apply the reflection through the mirror plane that is perpendicular to the C4 axis, we return to the original configuration. So we have what we call an S4 improper rotation axis. So the S4 axis is rotate by 90 degrees, reflecting the perpendicular mirror plane, and I get back the same configuration. It is a very special kind of symmetry operation that you may not be familiar with. So let's see that again. Rotate by 90 degrees, and then reflect through the horizontal mirror plane, and I get back to my original molecule. So an X4 axis is where I rotate through 360 degrees divided by 4, so I rotate by 90 degrees, and then I follow that by a reflection in the perpendicular mirror plane. So that is the S4 axis. Improper rotation axes have the symbol S sub n. Note that ethane, for instance, has an S6 improper rotation axis. Objects can only have a certain set of point symmetry elements. If an object has a certain set, then we can describe all such objects as belonging to the same point group. How then can we determine what is known as the point group? This is important because molecules have a set of symmetry elements associated with them, and there are only a finite number of combinations of symmetry elements, and these form what is known as a point group table. And if I can identify the point group of the molecule, I know which table I'm meant to use. So I want to be able to identify the point group of my molecule. And what we've got here is a flowchart to help us do exactly that. Note that this flowchart is available in a document in the miscellaneous folder of the work bin on IVLE. We are going to be using this flowchart in just a little while, but in essence you simply take a molecule and follow the flowchart, determining whether the molecule satisfies the questions asked along the way until you have identified the point group. Another way you can identify the point group is by inspection. The symmetry is related to the shape of the molecule, so you can use a chart like this to basically look at your molecule and say, what does it look like? Does it have this kind of shape or that kind of shape? For instance, an ethene molecule would look like this, and so it has DNH symmetry and is in the n equals 2 column, so it belongs to the D2H point group. For some people this is obvious. Does a molecule look like any of these representations? If it is not so obvious, you can always use the flowchart. Let's have a try then of using this flowchart with different types of molecules. The first one here is hydrogen peroxide. This molecule does not have the trans symmetry associated with it that you might have predicted using VSEPR. VSEPR doesn't work very well, as I'm sure you already know by now. Quantum mechanics, however, predicts the shape of this molecule perfectly, and it has this kind of staggered structure to it. And in fact, the only symmetry element that this molecule possesses is a C2 rotational axis. So the question would be, what is the point group of this molecule? So once we've identified all the symmetry elements, all we have to do is go to the flowchart and have a look. Well, the first question asks, is it linear? Yes or no? Well, the answer here is of course no. So we go over here. Does it have 2 or more rotational axes? No, it only has 1. So we go down here. Does it have a rotational axis? Well, the answer is yes, it has a T2 axis. So we go here. This question asks us to select a rotational axis with the highest n, which of course would be our C2 axis. And then it asks, are there n C2 axes perpendicular to our C2 axis? Well, the answer is no, there is only one C2 axis anyway. So we go down here. The next question asks, does it have a horizontal mirror plane? The answer again is no, so we go down here. Does it have any vertical mirror planes? Again, the answer is no, so I go down here. Does it have any improper rotations? Well, again, the answer is no, and so I go here. So therefore my hydrogen peroxide belongs to the CN point group, and we've identified that N is equal to 2, so it belongs to the C2 point group. Let's try another molecule. What about my trans dichloroethene molecule? This molecule has a C2 axis again here, but it also has a horizontal mirror plane. Well, let's go to the flowchart. First question asks, is it linear? Again, the answer is no. Does it have two or more rotational axes? Again, the answer is no. Does it have a rotational axis? The answer is yes. Select the rotational axis with the highest n, then does it have n C2 axes perpendicular to it? Well, no, it doesn't. The next question asks, does it have a horizontal mirror plane? And the answer is yes. So therefore it belongs to the CNH group of point groups, where n from this molecule is equal to 2, so my trans dichloroethene molecule has C2H symmetry. I will do one final molecule, and that one is phosphorus pentachloride. Well, for this molecule we have a C3 axis, we have 3 C2 axes, and we have a horizontal mirror plane, as well as several vertical mirror planes. So let's have a go at this molecule. The first question asks, is it linear? And the answer is, of course, no. Does it have two or more CN axes where n is greater than 2? And the answer is no. It only has one CN axis where n is greater than 2, and that's the single C3 axis. So we go down here. Does it have a rotational axis? Well, yes, it does. Select the principal axis, the rotational axis with the highest value of n, so that would be our C3 axis. Are there 3 C2 axes perpendicular to it? And yes, there are. So we go over here. Does the molecule have a horizontal mirror plane? And yes, we do. So therefore it belongs to the set of DNH point groups. N is the principal axis, which is 3, and so therefore my phosphorus pentachloride molecule belongs to the D3H point group. The remaining molecules are boron trihydroxide, ethane and tetraphenyl methane. I will illustrate the identification of the point group for tetraphenyl methane using the 3D MolSim software in class on Thursday. Well, this is the end of part 1 of this week's online lecture. Please continue on to part 2.